Hi everyone, welcome to Beyond Space event at the Tundra. In today's episode, we'll talk about a very interesting and surprising discovery that we can call a simultaneous baby boom of new stars. A team of astronomers led by Charlotte Olsen of the Rutgers University has recently found that 36 different dwarf galaxies far from each other experience a simultaneous change in the stellar birth rate. How is that possible? We'll find out today as our next guest is Charlotte Olsen. Hi, Charlotte.
Hi, thank you. I'm very excited to be here.
Very excited to
So
host you. And yeah, okay, if you can explain to our audience how is that possible and what have you found what is it all about?
Yeah, I'd be happy to do as much as I can. I don't know for sure if I have an answer as to how it's possible yet.
Yeah.
This is a really exciting kind of open question at the moment, which is pretty neat. I might talk a little bit about the motivation behind this, just because though I know a lot of the participants are probably fairly familiar from interests much like my own about the universe and how it kind of how it works and how we try to discover how it works. And
well, interested in this, yeah.
Yeah, so I work with galaxy evolution for this exact reason. I'm interested in seeing how the universe has composed itself over time. And the way that I look at that is by looking at how galaxies form their stars over cosmic time. And so this that is called a star formation history of a galaxy. And you can look at star formation histories of many galaxies through observations by looking at them and then figuring out how old the stars in the galaxy are, essentially, in order to trace kind of what they're doing. And this is really important because getting from a big cloud of gas to a whole bunch of stars and dust and things like that in a galaxy, and of course a big dark matter halo around it, there are a ton of different physical processes that are involved. And being able to pick those apart is really hard. And star formation, since the stars are formed from the gas, is a really good way of tracing that evolution. So that was kind of the motivation behind this. Is let's look at some star formation histories. Other people have done this. What we did with this one is there are two main different ways of reconstructing a star formation history for a galaxy. One of those uses resolved images, so where you can actually see the individual stars. And as you can imagine, the ones that are using resolved images, those have to be galaxies that are fairly close. You have to be able to see the individual stars within them. And so that limits the number of galaxies that we can look at. There's another way where you essentially look at the integrated light at different band passes, which is just a way of saying a different filter of color over different wavelengths. So for example, with our cell phone cameras, they're optimized for visible light. With the telescopes that we are using for this, we're using both space-based and ground-based telescopes that go all the way from UV down to the near infrared. So near infrared, that gives us information about the any of the hot dust, or infrared gives us information about the dust in the galaxy, because the dust will it'll kind of, when it's in a cloud in front of the hot stars, it'll then get all warmed up and it'll re-radiate. The UV is going to tell us about the youngest stars, and then the optical kind of in the middle, that traces the overall age of the stellar population, and it gives us some of the information about also some of the older stellar populations. So that's called SED fitting. It's spectral energy distribution fitting. I feel like this would be better if I illustrated it, and you do actually have a tablet or something.
You are allowed to, share some slides if you want to.
Okay.
Okay.
I didn't put together any slides. I
Okay.
have like maybe one slide,
Yeah.
but maybe if I
That's
could
great.
draw a little picture. Okay.
Okay.
All right. So let's see. Do that. Okay. Can you see my
Yeah.
iPad? Yes. Okay. Great.
I see.
All right. And I'll close that. Okay. So basically, with an SED, you take the light from a galaxy, and this is kind of, put this away. And this is the wavelength over here.
Okay.
And it's like when you have a prism and you spread out light over it. And so you get a spectra like this, right? But then when you're observing in bands, you're looking at your little galaxy, right? Like so. And then you're going to be observing maybe in the UV in a couple of places. And then maybe you're going to take pictures of it over in the infrared or in the optical. And then maybe some over in the infrared, right?
Yeah. So we need all the electromagnetic spectrum to get a comprehensive view of these galaxies, right?
Yes, exactly. Because then you can kind of decompose everything that's in there and be like, okay, well, I know this over here is dust. You know, this tells us about dust, and this is our young stars, right? So that's where it and then we have other things in there. So that's how it helps with the I'm going to with the other technique that is called the CMD method. That's not what I want. The other technique, which is called the CMD method, it is just looking at the individual stars. And since the stars have a relation, as you may know, of where you can look at the temperature and all of the different things, and that tells you some of the information about it. You can actually plot the stars that you observe in an individual galaxy. And this is, let's see, our, you know, a magnitude here, some sort of temperature, some band, and then you have a color over here, which is a ratio. I'm sorry, can you see this?
Yeah.
Okay.
It's
a terrible plot. So
yeah. Yeah.
So with this, all you have to do is say, okay, you know, these ones over here might be my young stars, and these ones are kind of the smaller stars that live a long time. And you basically, you break up your observation into a grid, throw it in time bends. So maybe this is not the most exciting demonstration of you know, what the two methods are, but I think it's kind of important to say, hey, you know, we have these two different types of observations. You know, do they agree? And that was kind of the thing going in. And we found a sample, or there is a sample it's far enough away to where, you know, you can get the broadband photometry, you can get each of the galaxies in a single image, right? But it's close enough to where we actually have information about the star formation histories from the individual stars. So it's important that we have these two at this perfect kind of distance, because the two have such different methods that when they agree on this, it's showing something that's really, really crazy. And so this sample of galaxies, they're very, very, very far away from one another. They're far out, they're about starting at 1 megaparsec and going out to about 4 megaparsecs away from us. So they're quite far from us, and they're spread out from one another. Some of them are close in groups, and some of them are separate. Right?
So, how did you galaxies? Those particular ones, like you said, far from each other, different. I don't know, different types of them. What was the key to choose those dwarfs?
So They happen to be, the area that they occupy is called the local volume. And the local volume is, it's outside of our local group, which is mostly just us and Andromeda and the dwarf galaxies that are near us, like the ones that you can see in the southern hemisphere, like the Small and Large Magellanic Cloud. Those are part of the local group, as well as a whole bunch of other ones. But the thing that is interesting about the local volume, it's a little bit further out and a little bit less studied, but we can still see a lot of those smaller galaxies as well. And those smaller dwarf galaxies are, we believe them to be really important because they're very important for galaxy evolution. They're some of the most numerous and probably the least understood because they are hard to observe because they're faint. But since they're small, they can get bullied really easily. So they're very sensitive to the environment that they're in. So this made this, it made the sample really perfect for this. And so we used this sample and we picked the ones where we had the best set of observations, the broadest set of wavelengths, so we could, best constrain what their story was this entire time. And that's how we chose, because dwarf galaxies are very, very small and very strange compared to especially our galaxy. But a lot of them live some of them live on their own, completely isolated, far away from other galaxies. And some of them are what are known as satellite galaxies, where they exist inside, for example, the Small and Large Magellanic Cloud exists inside the Milky Way's dark matter halo. So whatever the Milky Way is doing, it could potentially be influencing them, right? That could mean stealing its gas, disrupting stars, things like that. It's kind of like the Milky Way or the central galaxy in a dark matter halo is kind of it's the playground bully, right? And if that's one way of kind of thinking about it. And that's how you can get star formation histories that look a lot like, sorry, my dog has decided to exit the room right now.
He also wants to take part. Yeah.
Exactly. But that's how you can get star formation histories that are kind of similar to one another is, if there's a bunch of galaxies that are growing up in the same neighborhood that are under the influence of, some big schoolyard bully, then they can have their star formation suppressed at the same time or something like that.
Yeah, so like small and large Magellanic Clouds should have I don't know, similar star formation rates, right? Something, star formation history, let's say it, that they are connected. But in your research, you're saying that dwarf galaxies far from each other can have a similar trend in star birth rate. It's something like it's something so surprising, unusual to assume that.
Yeah, and your interpretation is absolutely correct, and it's a huge surprise. These galaxies are not, some of them
not connected with
a halo, and some of them are so far from one another, or they're in a completely separate halo, to where they do not have causal contact with one another. And wouldn't, they would not be able to communicate if they were to pick up the phone, so to speak, and call another galaxy and be like, hey, I'm going to stop forming stars right now. You should stop too. They wouldn't even be able to do that because that signal, that phone signal, would have to still travel at the speed of light.
Yeah, but it looks like this.
Yeah.
Just come up with the idea to
Yeah. Yeah, so I have one figure I think I can show, which is it's a plot, which most people don't love plots as much as I do, but it's the key finding, and it's pretty exciting. I can show how we're comparing, basically there's two different types of shapes here, if you can see this. One of them is kind of a boxy shape, and one of them is a smooth curved shape. And the curved one is the SED fitting one, so that's the integrated light at multiple wavelengths. And the boxy one is what we get when we take all of the individual stars and we put them in bins of time. So the x-axis here is time, and this is look back time, so it means right now is 0, and this 12 is 12 billion years ago, right? And so the y-axis is just showing for if we normalize all of these galaxies and then look at the median of them. If we just look at, if we look at scaled what the shape of them is over this entire time, this is showing what that is telling you about the trends increasing and decreasing for the entire sample. And the thing that is strange about this is that they all seem to decrease in this area between 4 and 6 gig years ago, and then they start to increase again. There is a difference between the two methods, but we made fake photometry from this black curve. So we made fake filters for and then fit that SED from this black curve, and that's the blue line here. So that shows, the blue line shows how good the method can match the black line. So there's a difference slightly in between the two methods as far as how they are able to, or how they interpret the information. So that the way to interpret this figure is that since the red and the blue line up so well, this is as good as we're going to get as to recreating the black line. So that means that the two methods, which come from two different types of observations and use two different things, they actually agree on this really super weird thing. So it's a very bizarre thing. So,
it clearly shows that there's a correlation. Yeah. How
Yeah.
can we explain this? We have so many ideas and explanations, scenarios that could explain this behavior, like our trend in those dwarf galaxies.
I don't have a full explanation yet.
Yes,
I can ponder. There are a bunch of different things that it could be, and I'm hoping that the fact that this is so unexpected really motivates a lot more people looking into this, especially in the local volume, because we are going to get some. I think the Nancy Roman telescope is going to be really good for looking at these galaxies, as well as James Webb. But there could be potentially some large scale environmental thing that's happening, like a big filament of gas coming in. No idea. This is wild speculation. There could be some sort of thing that's happening that's maybe preheating the gas in these galaxies early in their history or shortly after the age of reionization. Don't know. It's possible that the reason why we're seeing this is because our models for cosmology may be wrong. And maybe we need a different type of cosmology other than, lambda cold dark matter. I don't know if I like any of these explanations. There are more potentially, but I think it's really exciting because this offers an opportunity for us to really explore this, because I don't like the idea that our neck of the woods in the universe is special in any way. But it seems to be implying that it is right now.
Yeah.
So that means we need to look into it more, right?
Yeah, yeah. So it's a mystery to be resolved, and it motivates. I think it will motivate you to explore further this topic. And Charlotte, we'll be wrapping up this interview. Thank you so much for all your answers for this interesting lecture that you have explained to the audience all about your research, your recent discovery. Once again, thank you so much, and good luck with your further research on this.
Thank you so much.
Thank you so much. It was a pleasure to host you. Thank you. Bye.